we've carried on our journey of quantum mechanics and we've looked at the Schrodinger equation. We've explored the uncertainty principle. We've looked at wave functions and probability densities. We've also looked at an infinite well. And an infinite well, we've seen the effects of confinement, and that this leads to the invariable principle of quantization. And finally, we started to explore obstacles and potential barriers and wells. For example, we can have a potential landscape in which there is a step in the potential. This is my x-axis. This is my potential energy for a particle. I could have a depression in the potential. I could have an obstacle. And I could have all kinds of changes in potentials. I can have a ridge-like structure. I can have a structure like this, so the potential energy is constant, and all of a sudden I have a certain slope. Then I go back up. I could have variations in the potential landscape. And my device, with whatever I'm building, whether it's a natural device or an artificial device, will pose a problem of this kind. So all of these are possible variations of the potential energy as a function of x. And once you have a knowledge of this potential energy, you can place this potential energy in the Schrodinger equation, solve the Schrodinger equation, find out the wave functions, and then you can determine the probability densities and the probabilities, because those are what matters to an experimentalist. Alright, let me give you some more examples of potential energy functions. In a solid, you have atoms. Suppose I just consider a one-dimensional solid. So it's a nanofiber, one-dimensional, and it's a metallic solid, which means that there are free electrons wandering around inside this chain. The metal as a whole is neutral. Everything has to be neutral. So, where are those free electrons coming from? You know that a metal conducts. So how does a metal conduct? It conducts because it has free electrons that do not belong to any atom, that have been freed from the confines of the atom, and they can roam about inside the bulk of the solid. So there are free electrons everywhere. However, the metal as a whole is neutral. So these atoms are in fact ions, positive ions, which have donated their electrons to the sea of electrons inside metal. So these are ions. And ions are positively charged because these are atoms that have been stripped off from their electrons. Now you have electrons wandering around in this fixed rigid array of positively charged ions. And when an electron comes near an ion, its potential energy drops because the electron is negatively charged. So if I plot the potential landscape for this array of atoms, close to an ion, the potential energy has to go down. Away from the ion, the potential energy is constant, but close to the ion, the potential energy drops. Like this. Then away from the ion, the potential energy remains constant. You see the next ion, the potential energy for the electron once again drops. So now I have an arrangement inside this one-dimensional solid in which the potential energy is lowered near the ions, because the ion is positively charged. And the electron would like to live close to the ion. It lowers its energy in that sense because both of them are oppositely charged particles. So you can have an arrangement of this kind. This is a simple model of how an electron behaves inside a solid. Instead of having an infinite well in which there is a single electron, you have a large number of electrons in a solid and they see a potential of this kind. This yellow curve is the curve that represents the potential energy of an electron, a free electron inside a one-dimensional solid. Alright? This is one example. Another example, I take the hydrogen atom in which I have a nucleus which is positively charged, and suppose I have an electron in the vicinity of the nucleus and the electron is at a certain distance r. Now I would like to plot the potential energy as a function of r. If the electron is close to the nucleus, the potential energy goes down. So if I plot the potential energy with respect to r, this is what it's going to look like. This is my r, which is the distance from the nucleus. This is a graph for my potential energy for the electron. So closer to the nucleus, the potential energy has to go down. And if you're far, far, far away from the nucleus, the potential energy is zero. Because the electron is not within the confines of the nucleus, it is unaffected by the nucleus. So a plot that can represent the potential energy of an electron looks like this. Away from the nucleus, the potential energy approaches zero. In other words, the atom is ionized. The electron is free. Potential energy zero means a free electron. And if the electron is coming close and close and close to the nucleus, its potential energy goes down. And it goes down like this. And there's a mathematical relationship that actually tells what this potential energy is going to be. And that you learn from electrostatics. The potential energy as a function of r is given by minus 1 over 4 pi epsilon naught Ze, where Z is the atomic number, the number of protons inside the nucleus. This is the charge of the proton, it's E. I multiply this with the charge of the electron and divide by R. This is just Coulomb's law. With R squared replaced by R, if I take the derivative of this, I will get the Coulomb's force. You don't have to remember this, by the way, but this is a graph of this potential energy curve. This is Coulomb's law. I take the derivative of this potential energy, I will get the force. So there are different kinds of potential energy landscapes. In the infinite well, the potential energy landscape looked like this. The potential energy is infinity, really large outside a certain confine, and an electron or a particle is trapped within inside this well. This is the potential energy landscape. And we figured out that the energy levels inside this infinite well, they become quantized. Another frequent example which is employed in physics is that of a harmonic oscillator. Now, harmonic oscillator, most of physics, by the way, is about harmonic oscillators. When you're in your freshman year, when you're in your FSC or A level, you see a harmonic oscillator, which is called a pendulum. When you get to university level physics, you'll see more sophisticated developments of the concept of harmonic oscillator. An atom that is vibrating inside a solid acts like a harmonic oscillator. The spring is the electrostatic force between atoms. String theory is the culmination of the concept of harmonic oscillators. So the building of physics is actually more and more sophisticated, progressively more sophisticated developments of the concept of harmonic oscillator. You can treat light as a harmonic oscillator. This is a very universal and embracive concept in physics. Now for a harmonic oscillator, let me give you a simple example. If I have a mass which is attached to a spring and tethered to a solid support, the mass is m, the spring constant is k, then I know that this object will have a certain potential energy and kinetic energy. The potential energy for this object, so there is a certain resting position, which is the equilibrium position. I can displace this mass to a distance x. So there is going to be a potential energy as a function of x. Now what is this potential energy? It's half kx squared. Now look at the potential landscape. If I plotted this potential energy with respect to x, what kind of graph would I obtain? It's going to be a parabola. This is the resting position or the equilibrium position, and as you go away from x, the potential energy increases. So if I pull this mass away from the support, its potential energy is going to go up in a parabolic fashion. Now if I take this potential energy and put it inside the Schrodinger equation over there, I will get a different level of quantization. In that case, my energy levels are just going to be equally spaced inside this well. Here my energy levels are not equally spaced. The energy levels grow as n squared. Here my energy levels are equally spaced, and the energy levels are given by n times h bar omega, where omega is simply the separation between any two energy levels. This is h bar omega. So in a harmonic oscillator, the energy levels become equally spaced. And this is a fine example of doing physics. This is a toy example. Most of the physical phenomena that you observe can be described by the model of the harmonic oscillator. So you can have an electron in a level. If it is given the right amount of energy through thermal means or through a photon, it can be promoted to an excited level. It can fall from an excited level to a lower level and emit photons while conserving its energy. So how does this come about? This comes about because we take this potential energy and plug it into the Schrodinger equation, and then use the machinery for solving differential equations and find out the solution. And it turns out that the energy is once again quantized. Now with these examples, I would like to go on further. And what I would like to do now is, I would like to turn to the concept of obstacles and tunneling and try to give you an idea of how do obstacles affect transmission and reflection. I already talked about light. Light acting, impinging on a certain interface. I have air here, and I have, say, glass or water here. And as light comes in, falls on the interface, it can either be reflected or it can be transmitted. Of course, it changes its angle as it is transmitted because of Snell's law. Now suppose this incoming beam of light is a quantum beam, which means it comprises just one photon, right? I can have one photon coming in and impinging this interface. Now what's going to happen to that photon? Is it going to be reflected or is it going to be transmitted? This is just analogous to the example of a beam splitter. I have a 50-50 beam splitter and a single photon comes in. There's a certain probability that it will be transmitted and a certain probability that it's going to be reflected. It's exactly the same problem here. Now, how do we determine whether this photon, single photon, is going to be reflected or is going to be transmitted? And if it is transmitted, then that single photon is going to change its direction. Now, all of these are strange, become strange effects when you look at these from a quantum perspective. Now, what we would like to do is we would like to rejuvenate our discussion of obstacles. We've already seen obstacles, and we'd like to describe this phenomenon in terms of obstacles. One thing that is immediately clear is that if a certain intensity of light is coming in, and if this intensity is being split up into two parts, then the sum of this intensity has to be the same as the sum of this, and this intensity has to be the same as the sum as the incoming intensity. Because the intensity is split up. It's not necessarily equally split up, but the overall intensity cannot go up unless you have some kind of amplification, which happens in a laser. So this intensity has to sum up, which means that if some energy is transmitted and some energy is reflected, then the sum of these intensities has to be equal to this intensity. That's what we would like. That's our physical intuition. And we would like to see if that holds true in the quantum scenario or not. Now we have an obstacle. Can you hear me? I have to speak very loud because this microphone system is not really working fine. Can you hear me at the back? If you're listening, I hope you are. So I have an obstacle. A potential step. This potential energy, let's take this to be 0. And here there is a step of height E naught. And I have an incoming particle of certain energy E, which is less than V naught. Or sorry, let's look at a simple example. The energy is bigger than V naught. Now this is my first region, this is my second region. In the first region, I know that let's first of all plot the wave functions. We can do that without recourse to the Schrodinger equation, and we've already done that. In this region, the difference between the energy and the potential energy is large. So K is, the kinetic energy is large, K is large, wavelength is short. As soon as you cross the boundary, the energy is bigger than the potential energy, so you can indeed cross the boundary. What's going to happen is that the separation between the energy and the potential energy is going to go down. The kinetic energy is going to go down. The K is going to go down because the momentum is going down. The wavelength is going to go up. Now, in the previous lectures, I've drawn the wave function to look like something like this. Now here the wave function is larger. This is the wave function. Here the wave function is smaller, shorter. K is large and smaller here, but the wave functions are the inverse of K. So this is K1, and we know that this K1 is simply 2me over h bar. Agreed? And this K in this regime is 2me minus V naught over h bar. Now V naught is bigger, so this thing is small, K2 is small, the wavelength is large. Now I've drawn this amplitude to be larger. It could be smaller as well. Now I would like to find out what happens to the amplitude. Now these equations come out because we solved the Schrodinger equation. In this regime, the wave function is given by A, EIKX. K k1x plus b e minus I k1x. In this regime, the wave function is simply given by all right? No? Why? Yeah? This I tackled in the previous lecture. So this is the solution of the Schrodinger equation. Inside this regime, potential energy is 0. This is a wave that is propagating to the right. This represents a wave that is reflected from the interface and propagating to your left. In this regime, I have a wave that is going to the right and a wave that is coming to the left. However, the physics dictates that I do not have this backward propagating wave in this regime because the particle is going from the left to the right and there is no obstacle to the right of this interface to reflect back the particle. So this is from our previous lecture. Now we would like to find out what is A, what is B, and what is C. How much is A, how much is B, and how much is C? That's what we would like to find out. Because we would like to find out, we know the wavelengths here, but we don't know anything about the amplitudes. Now this potential step is finite, it's not infinite. So we have certain conditions that are imposed on the wave function. The first condition is that the wave function has to be continuous, right? It cannot abruptly change. Because abrupt changes in the wave function means infinite energies, and no particle can have an infinite energy. So the wave function has to be smoothly varying. It cannot abruptly change here. Suppose this point is x equals 0. I put my interface at x equals 0, which means that the wave function at x equals 0 on the left side must equal the wave function on the right side at x equals 0 at the boundary. So if I put x equals 0, this becomes a plus b, and this becomes c. Because there's a 0 here, this becomes e raised to power 0, 1. Now, yes?
Well, sir, can you please repeat why d is cancelled?
Now if you look at this wave function here, if I write a wave function of this kind, this actually means kx minus omega t, because there is a factor e raised to I minus omega t that is suffixed to the wave function. That's always there because that comes out from the time dependent part of the Schrodinger equation. It's always there. Now if I compare this wave function with this wave function, in which this plus iota is replaced by minus iota, then I plot the real parts of these wave functions at different times, then this wave function would represent a function that is progressing to the right, moving like this, which has a positive speed, whereas this wave function was going to represent a wave, a traveling wave that is propagating in the negative direction. Now here this term is 0 because this backward propagating wave is coming from some interface. If I have a particle that is moving to the right, to your right, and the particle doesn't see an interface, it's never going to come back. So I have a particle that is launched into this problem from the left, and it sees an interface, and beyond the interface there is nothing to reflect it backwards. That's why the physical insight tells me that this term is going to be 0. Here there is a backward propagating wave because there is an interface and there is the possibility of reflection of the particle. Alright, so one of these requirements of the wave function gives me a constraint between A, B and C. So now if I know any two of them, I can know the third one. Alright? So my goal is to find out these constants, A, B and C. Now if I know any two of them, I can know the third one, because I have this constraint equation. Now there's another constraint equation. The derivative of the wave function has to be smooth. It cannot abruptly change because it's not an infinite well or an infinite boundary. So if I take the derivative of this side and I take the derivative of this side and I equate them at the boundary, I can do that. So if I perform this derivation, I get AK1 A minus IK1 B equals IK2C. This is the condition that the derivative is continuous, and I put x equals 0 and I get this relationship over here. Now these i's go away and I'm left with K1 over K2 A minus B equals C. Now I have two equations, two constraints, and with the help of these two constraints and three unknowns, I can determine one of them with respect to the other. I can eliminate two of these constants. What I could do, I could express B in terms of A, and I could express C in terms of A. Now if I look at these equations and I just equate the two C's and I say that this object equals, let's call it beta. If this object is beta, I have beta A minus B equals A plus B. This gives me beta A minus A equals beta B plus B, which means B over A Alright, so B over A equals K1 over K2 minus 1, K1 over K2 plus 1. This equals K1 minus K2, K1 plus K2. What I determine is B in terms of A. So if I knew A, I can tell the ratio of B and A. I can tell how much is the particle reflected. What's the probability that the particle is reflected? And I'm going to delve on this in a minute. Anything problematic about this derivation? Yes. Anything is alright? Now I can also determine C over A. Could you please find C over A? Please determine C over A. So C over A is 2 beta over beta plus 1. I have found C over A. Let me rewrite B over A. So if I knew A, which is the amplitude of the incoming wave, I could tell what is B, what's the amplitude of the reflected wave, and I could tell C, what's the amplitude of the transmitted wave. Now what about probabilities? How do probabilities relate to amplitudes? That's the question. These are amplitudes in a wave function. I would like to ask, how do probabilities relate to amplitudes? Now if I have an incoming photon, a single photon, I would like to find out what's the probability that the photon is reflected. If I knew B over A, from this probability, from this amplitude, the ratio of amplitudes, can I determine the probability that the particle is reflected? Is it going to be equal to this? Now what is an amplitude? An amplitude doesn't have a meaning on its own. You take the modulus squared of an amplitude to get a probability density. So if I have a wave function, this wave function on its own doesn't mean anything. You need to take the modulus squared of this wave function. Psi modulus squared, and that will give you probability density. Now suppose I have this interface and I have an incoming photon. Whose wave function is given by this expression, and I would like to find out the probability that this photon is reflected from the interface. So what I'm doing is I'm observing. So what I do is I stand here and I observe. So this is my detector observing the photon, and I'm looking at any photon. So I make an imaginary surface and I see how many photons are coming through this surface in the backward direction per unit time. Okay, that's what I would like to see. So I have photons coming in per unit time, which means I have a flux of photons. Flux means per unit time. I have some photons coming in per unit time, and I'm looking in the backward direction. I'm looking at the back plane of the interface, and I'm seeing how many photons are moving through this interface in the backward direction per unit time. So I need to find out the probability flux. Alright, so what is the probability flux? The probability flux means, first of all, I need to know that there is a photon. And the probability density that a photon exists is proportional to B modulus squared. So higher B, greater will be the chances of finding a photon coming in the backward direction. It's not B, it's B modulus squared. Because B modulus squared is a probability density. It's not B. So B can be complex number. I take the modulus squared, I get the probability density of finding a photon in the backward direction. And I take D, I don't take A or C because I'm looking at the reflected photons. However, it's also possible that I get more photons per unit time. More photons I will get per unit time if the speed of the photon is larger. So I have an incoming beam of photons, but they are single photons coming in one after the other, coming in tandem, one after the other. If there are more photons coming in per unit time, which means there's a higher flux of incoming photons, I might see a higher flux of reflected photons. So higher the speed of photons, higher will be my probability flux. Per unit time, I will see a larger number of photons. So I need to multiply this B modulus squared by something that is proportional to the momentum. And the momentum is simply H bar K1. So this is my reflected probability flux. Yes. So, okay.
What if a single electron is going, would it be less than a single electron goes as the momentum increases?
Suppose I have capital N photons coming in. Capital N photons coming in, 1000 photons coming in, 100 photons coming in, 3 photons coming in, 1 photon coming in. So this N represents the number of incoming photons. Could be 1. Okay? Now the probability flux, how many photons, what's the probability that I see a reflected photon per unit time, and how many of them would I see, would depend upon N. Higher the number of incoming photons, it would depend upon B modulus squared, which is the probability density for the reflected wave of a single photon, and I'm multiplying it with the number of incoming photons multiplied with the speed of the reflected photons. So this is my reflected probability flux. Now what is my incident probability flux? Can you speak up? What's the incident probability flux? A modulus squared H bar K1 N. This N is just a scale, it's just a normalizing factor. Now the transmitted probability flux. C modulus squared. What else? What next? H bar K2 N. This N could be 1. So I could have a single photon. Now I define the reflection coefficient R. Is the probability that a photon is reflected is given by the reflected probability flux divided by the incident probability flux. Okay? And that turns out to be B modulus squared over A modulus squared. So the reflected probability, the probability that a single photon is reflected, or the average number of photons that are reflected, the average fraction of photons that are reflected from an incident beam of photons or electrons is given by R, capital R. It's not B over A, it's B modulus squared over A modulus squared. Let me finish. And this turns out to be, now I've already determined B over A. It's beta minus 1, beta plus 1 whole square. So it depends upon K1 and K2, and it depends therefore upon V naught. K1 minus K2, K1 plus K2 squared. And I could also write this in terms of V naughts and E's. Alright, I can do that. This is just algebra, I leave it to you. Now if I take the transmissivity, or the probability that that single photon is transmitted instead of being reflected, that's going to be C modulus squared over A modulus squared, but C modulus squared comes with a K2 and A modulus squared comes with a K1. The n's are just cancelled out. That means n is just a normalization factor. It determines the total flux of photons. That could be 1 as well. And if I work this out, this I've already determined C over A, that's 2 beta or beta plus 1. So I have 4 beta squared, beta plus 1 squared, K2 over K1 is 1 over beta, so this becomes beta. Now if I were to add this with this, I will get 1. R plus T equals 1. Yes. Speak up, please. K is proportional to speed. Momentum is proportional to speed. Speed is per unit time. Distance per unit time. Probability density is per unit distance. So the distance is cancelled out. Yes. So it depends on the ratios of K1 and K2. It does not really depend upon how much is K2, it depends upon K2 over K1. And you can plot, if K1 is fixed, you can plot T versus K1 or T versus K2. Now you can have a similar problem. Okay, let me first answer the questions. Yes?
Will A always be bigger than B in this case?
K?
A always be bigger than B in this case?
Not necessarily.
Okay.
Suppose I have, very good question. If I have a potential obstacle, looks like an obstacle, but quantum mechanically it is an obstacle, doesn't look like an obstacle because it's a depression in the potential. The potential is actually going down. This is my energy. A particle is launched from this side. Now quantum mechanically, this particle, even though it's going downhill in the potential energy, still it can be deflected. Whenever there is a change of medium, there is a change in the potential energy, it's like the particle is akin to entering a different medium. There is an interface. That's a quantum interface. And at that interface, there is the likelihood of reflection. Now in this particular case, beta, which we've defined as K1 over K2, is now less than 1. Because K1 is now shorter than K2, which means that the wavelength is larger here. And it's smaller here. And the amplitudes can also change. They can go from big to large or large to big, depending on ratio beta. Alright? And there were more questions. Yes.
So I don't completely understand how you derived R and T.
How to derive?
How did you derive R and T?
R is defined as the reflected probability flux over there divided by the incident probability flux. That's how we define reflectivity. How much intensity is being reflected divided by how much intensity is coming in. So I've just substituted those expressions in here. Likewise, for transmissivity or the transmitted ratio, how much intensity is going out, how much flux is going out, is being transmitted versus how much flux is coming in. Alright? More questions? Yes? Capital B? Okay, so can you think of a scenario in which this object is greater than 1? No. Unless you have something really funny going on with complex numbers. Okay? More questions? Yes. Alright, let's try to relate this with the classical picture. Suppose this is my potential step, V0. And the incoming energy is smaller than V0. Alright? Once again, there is the probability of reflection. And there is some probability that the wave function might be found in this forbidden region. We've looked at this already. So there is an incoming wave, and then there is a decaying wave inside this region, like this. Agreed? And how does this decay come about? It's not oscillatory here, it comes out because we solve the Schrödinger equation. Alright, now for this incoming photon, there's a barrier and there is a certain reflection probability and a certain decay inside the classically forbidden region. Now this decay is over some length scale delta. And we've already found that delta. This delta was equal to h bar over 2m V0 minus E. In this regime, the wave function is given by e raised to power minus x over delta. Delta is the penetration length. It tells you how much the wave function can leak into the classically forbidden region. Okay, and we derive this, so please check up your notes. I don't want to do it again. This is the penetration length. Now, how do I define the penetration length? If x equals delta, which means that my x is equal to this penetration length, then the function has decreased by 1 over e. At x equals delta, the function is e raised to power minus 1, which is 1 over e. And if I plug in the value of e, which is 2.718, I get 0.4, roughly. So at this length, the wave function decreases to 40% of its value at the interface. So it's a measure of the penetration length. It's just one measure of the penetration length. And this delta is equal to this. Higher the penetration length, the wave function can leak in over over a larger extents inside the classical forbidden region, it can go further out to the classical forbidden region. If delta is large, the wave function goes further out. If delta is short, the wave function quickly dissipates in the classically forbidden region. When is delta short? When is this small? This is small when this object is large. Which means that now when is this object large? When this difference is large. Which means that either this potential barrier can be large. If I make bigger potential barriers, the difference between the energy and V0 becomes large, and this wave function will now decay rapidly inside the classical well. This is intuitive. Now we talk about quantum intuition. In quantum intuition, if you make the barrier large, the penetration inside this classical forbidden region is going to be shorter, smaller. Or if the incoming electron has a smaller and smaller energy, would the penetration be smaller? Now the question in this particular scenario is the following, which my friend asked over there. Why don't we see this in the classical world? I have an incoming particle with a certain energy, and it sees a potential barrier, and the barrier is not sufficiently strong. The particle can still penetrate into the other region because the potential barrier is not strong enough, right? Not strong enough here. And there is some finite probability here that the particle is reflected. This is the probability. Why don't I see this effect happening in real life? I have a cricket ball which strikes, I have a cricket ball that is impinged on the surface of water in a pool. Why doesn't the ball reflect from the surface of the pool? Why does it always go back in? Why is it not reflected? Why don't I see reflection for classical objects? The reason is the following. What I've drawn over here is, do you understand the question? Why don't I see reflection for classical objects hitting an interface? Right. So a wall can be approximated as something that's bigger and bigger. The potential barrier is large. But what if the ball is going from one kind of medium to another kind of medium? For example, I have a table tennis ball and it's in water and it sees an interface of oil. Now there is a certain probability that that ball there might be classically a probability that this ball is reflected, but I don't see it being reflected. The reason is that this diagram that I've drawn over here is slightly problematic. I've drawn the potential step here to be extremely sharp. Okay, so I can have potential steps of different kinds. So this is an ideal potential step. This is a non-ideal potential step. Whenever there is an interface in the classical world, the potential cannot abruptly change. It changes over a certain length scale. For example, if I have the surface of a solid and a photon is coming into the solid, then, okay, my question is why, the solid has a certain surface. The potential changes over the length of the surface. Now what's the length of the surface? The depth of the surface. It's the first layer of atoms on the surface, or the first two layers of atoms on the surface. Those layers have a certain width, a certain thickness. It could be of the regime of nanometers or angstroms, but it has a finite width. So this width is determined by the interface, by the real material. It could be of the order of nanometers. Now, an incoming particle has a certain wavelength, lambda. If this lambda is bigger than the distance over which the interface changes, then you don't see quantum effects. In order to see quantum effects, you have to get to the scale of the wave, which means that this depth has to be short enough, shorter than the wavelength of the particle, in order to qualify this interface as a potential barrier. So if your lambda is larger than this interface length, which is, say, let's call it d, then you would see quantum effects. However, if your interface depth is much larger than the wavelength of the particle, you don't see quantum effects. So the wavelength has to be finer. Sorry, the wavelength has to be bigger than the depth over which the potential changes. This has a certain width, a certain depth. The wavelength has to be larger so that this change in potential can negotiate with the wavelength of the incoming photon. If the wavelength is actually smaller, you don't see the graininess of quantum mechanics. You don't see the wave behavior of the particle, and you cannot see reflection and transmission. So this depth over which the interface changes has to be really, really small when you compare it with the wavelength. Let's take a 10-minute break.
आवाज नहीं आ रही है, बिल्कुल